Hello everyone, welcome to our low temperature thermochronology online lectures. Today, we'll be learning Chapter 9, Application Case 2, Thermal History Reconstruction of Sedimentary Basins. I'm Nitao from the School of Earth Science and Resources, China University. This is the QR code to my personal homepage. You are welcome to scan this QR code and you'll be able to find more about our lectures. Here is the outline of this chapter, and we will start from the section 1, introducing some terms and approaches. Here in this figure, it shows some principal types of thermal histories. Like for this one, it's a rapid cooling, and here is a reheating, and we have a slow cooling. And for all the three different thermal histories, the age will have different meaning. For instance, for the rapid cooling one, it will produce an age we call the formation age. And for the relatively small cooling, we'll have the age we call the cooling age. And in the case for reheating, the age will be apparent age, which means it is a mixed age, as is showing in this figure here. So, after we have been learning all the theories and methods of low-temperature thermochronology, I have a question. What do thermochronometers record? Okay, thermochronometers record either cooling age, which is the time since rocks were at a thermochronometer-specific effective closure temperature, and exhumation, that means the advention of rocks towards the surface of Earth. Erosion and exhumation are terms that are often misused and confused, so it is necessary that we need to start with some definitions. Exhumation is the unruffling history of a rock. The vertical distance of a rock moves relative to the Earth's surface. It can result from tectonic or surface processes. Denudation refers to the removal of rock by tectonic and/or surface processes at a specific point at or beneath the Earth's surface. Erosion, on the other hand, means the removal of mass at a specific point on the Earth's surface by both mechanical and chemical processes. Rock exhumation E is the result of the combination of rock uplift and surface uplift. Rock uplift U refers to vertical motion of rock with respect to the center of the Earth, and the surface uplift US is vertical movement of the Earth's surface with respect to the center of the Earth. The amount of rock exhumation a sample experiences will reflect both. The temperature change measured in the shallow crust, or we call it temperature or thermal gradient, is often used to study thermal processes in the crust. The geothermal gradient is simply the difference in temperature at two different depths in the Earth, with typical values of 15 to 30 degrees centigrade per kilometer. In this example, the geothermal gradient doubled over the first 15 million years of the calculation. Multiplying the geothermal gradient by the rock thermal conductivity will give us the surface heat flow. This figure shows the sensitivities of apatite helium, apatite fission track, and zircon uranium thorium helium thermochronometers. And we can see that the sensitivities of these thermochronometers overlap with the hydrocarbon generation zones. The application of low-temperature thermochronology to hydrocarbon resources, especially to petroleum exploration, will be further addressed in Chapter 8 and Chapter 11. On the basis of thermal sensitivities of the methods and the concept of partial annealing zone and partial retention zone, the principle of vertical age distribution is shown in the figure to the right, where we can see that thermochronological ages is actually a function of both temperature and elevation or depth. Plotting apatite helium age data with elevation is therefore useful when solving geomorphology evolution problems. Here are some good examples that you may refer for further discussion and study if you are interested. Here is an example that apatite helium ages on Oregon parallel 2,000 meters elevation transect in the Sierra Nevada compared with modern elevation profile. The general correspondence between the location of deep and wide valleys and higher helium ages suggests that helium ages were influenced by the fluctuations exothermals associated with paleocanyons located approximately where they are found today. This data suggests that reliefs of about 3 kilometers at 75 million years or a large mountain range by late Cretaceous time. The elevation profile can be related with more than one thermochronometer. As per what thermochronometers should be adopted, we need to ask questions like, what is the scientific questions you want to address? Can the helium method answer it? Are there any other age data, for example, fission track data? Are proper minerals in host rocks there? So, my suggestion is that a proper research plan is essential. During the development of detrital thermochronology, the lag time concept was proposed, and it means the difference between the age of cooling and the age of sedimentation after erosion. Please be reminded that there is an important assumption that the age of erosion is actually the age of sedimentation. In other words, the difference between the age of erosion and the age of sedimentation is neglectable. Multiple ages from individual grains could provide a detailed and ambiguous fingerprint of a source terrain. This is especially important when combining helium age data with uranium-lead geochronology data of detrital zircons. By doing so, we can build a single grain lead helium plot, give us important information about the provenance of the studied rock. Sampling along vertical profiles is a great strategy that allows for the determination of exhumation rate. The exhumation rate is calculated by dividing the elevation difference by age difference. Exhumation rate can only be detected by analyzing age-elevation relationships if no vertical displacement between samples occurred after cooling. This is an important principle we should be keeping in mind when we are trying to do an age elevation plot of a study area. Break-in slope of apatite fission track age versus elevation plot help us define the formal base of the partial annealing zone. This is quite useful when we're having apatite fission track age data along an elevation profile, and we are also having apatite fission track length data. So, what we have been talking about, all these methods are called altitude-dependent method, where more samples are collected along a vertical profile and dated with the same method. Mineral pair method is another very useful way of conducting low-temperature thermochronology study, where a single sample is dated with 2 or more different geochronological methods, for instance, with different closure temperature ones. This is a case study applying multi-method thermochronology, where many thermochronometers have been utilized, including from higher temperatures to lower temperatures, zircon-uranium light, titanite-uranium light, hornblende argon-argon dating, biotite argon-argon dating, plagioclase argon-argon dating, and low-temperature geochronological methods, zircon-helium dating, apatite fission track dating, and apatite helium analysis. Here is another classic example from the Alps applying multi-method low-temperature thermochronology, such as we can see from this figure that methodology utilized including muscovite argon, biotite argon, zircon fission track, and apatite fission track analysis. And from this figure, we can see that apart from apatite fission track age, apatite fission track length is also acquired in this study. One of the main advantages of mineral pair method is that one sample is often analyzed by different methods. For example, the commonly used ones including apatite fission track, apatite helium, zircon fission track, and zircon helium methods. Its disadvantages is to be based on the assumption of closure temperature concept, namely all ages are treated as cooling ages. Therefore, the paleogeothermal gradient must be determined, and the paleogeothermal gradient is assumed to be stable during the time of the cooling. The above the section 1 of this chapter. Thank you for your attention.